In today's lecture and in next few lectures, we shall talk about the describing function analysis of nonlinear systems. Basically, you remember that limit cycles are oscillations of fixed amplitude and period, and these oscillations are undesirable in many systems because these not only damage the mechanical structure but also associated with power losses. So this describing function analysis is one approach to analyze the existence of limit cycles. We have already studied some of the approaches to predict the existence of limit cycles. These approaches include the phase portraits. We can sketch the phase portraits of nonlinear system, and then we can study the existence of these limit cycles. We have also talked about some analytical approaches which are applicable to some systems. These are the index theorem and the Bendixson theorem. These theorems can be utilized to predict the non-existence of limit cycle in nonlinear systems. And the approach which we are discussing today and in next few lectures, that is the describing function analysis. This approach is applicable to nonlinear systems which can be described in this particular form. That is, major part of the system is linear, which is described by a transfer function, and then there is one nonlinearity in the system. Furthermore, for the prediction of existence of limit cycle, we take the input to be equal to 0, because if for input equal to 0, if there exists a limit cycle, then that will also exist for non-zero inputs as well. So the systems which can be described by this block diagram, those systems can be analyzed by this describing function analysis approach. So there are basically two categories of systems which can be brought into this particular form. One is that the system is almost linear and there is one nonlinearity in that system. Those systems can be brought into this particular form. And the second category of systems are genuinely nonlinear systems. So let's elaborate these 2 points. For almost linear systems, here is the most common situation. The process, the model of the process can be approximately described by transfer function in many cases, and the sensor, that is also in many cases can be approximated by a transfer function. And the actual nonlinearity in many systems is in the actuator. This is most frequently encountered nonlinearity, that is dead zone and saturation. Saturation is always there in real actuators, and in many actuators we also have dead zone. So this is the most commonly encountered nonlinearity in many physical systems. So what approach they do follow is that initially they just ignore this nonlinearity, design a controller utilizing the linear control techniques, because linear control techniques are well established and systematic approaches exist to design controller for linear systems. So what they do is that they design a linear controller based on linear control theory by just ignoring this nonlinearity. Once the controller is designed, then one of the effect of this nonlinearity is to create a limit cycle, and then that limit cycle is predicted by this describing function analysis approach. So you see that this block diagram is not the same as this one. However, by utilizing simple block diagram reduction techniques, this block diagram can be brought into this particular form. How? Let's see it. So this system block diagram is resketched over here. Everything is the same. It is only redrawn. A reference signal and subtracted by some another signal. Reference signal subtracted by another signal generates x of t. So we have this x of t. and then this is multiplied by GC of S, GC of S, and then you can verify that we have the same loop, which is this one, only we have redrawn it. Clear? For the purpose of analysis, we take this R of t to be equal to 0. So if this is 0, we can simply remove this summer, and in that case, this block, and this block, these three blocks are in cascade, and therefore this block diagram can be redrawn into this form: GC multiplied by GS multiplied by GP, uh, and then uh, these three cascaded and preceded by this nonlinearity, and then this u of t is added with a signal which is 0. This u of t is added with a signal which is equal to 0. So we can bring this system into this particular form. So this describing function analysis, one category of systems to which this can be applied is a set of these systems. That is, systems are almost linear, and these have some kind of nonlinearity over there. The second category of the systems which can be analyzed by this approach is genuinely nonlinear systems. Let's elaborate this point as well. So this is a nonlinear differential equation. The system is itself nonlinear, and we want to analyze this system utilizing the describing function analysis technique. For that purpose, we need to bring this equation into this particular block diagram. How to do that? So we simply rearrange the terms, the same differential equation, nonlinear differential equation, written here again. So x double dot minus alpha x dot is this term, x dot multiplied by minus 1 multiplied by alpha, and then plus x, and this thing alpha x square into x dot, that is brought to the right hand side. This product we can rename it. We can rename this product as another signal w. W is equal to minus x square into x dot, and then this equation is transformed into this equation: x double dot minus alpha x dot plus x is equal to alpha w, where w is given by this relation. Now this equation written in Laplace domain is given over here by taking the Laplace transform, by setting all the initial conditions equal to 0. This is the Laplace transform, s square x of s, and so on. And furthermore, we can take x of s common from this left hand side, and then the relation between x of s and w of s is given by this transfer function. That is, this can be described by this block diagram, where w of t, what is w of t? W of t is equal to this thing, that is, w of t is some nonlinear function of x of t, and then here we have x of t. So this multiplied by this negative sign, we have minus x of t, and then 0 is added with that one. So again here we get w of t. So what we have done is that this was some genuinely nonlinear equation. We have performed simple arithmetic to it to bring it into this particular form. So any question up to this point? In this system, we have also taken input to be equal to 0 for the simplicity of our analysis. You know that if you are, for example, solving the tracking problem, this input can be non-zero as well. However, we have taken it to be equal to 0 for simplicity of our analysis, because if limit cycle exists for this input, input equal to 0, limit cycle will also exist for some other input. For example, for step input, if this limit cycle exists for this input, limit cycle will also exist for a step reference input to that system. So this simplifies our things, taking r of t to be equal to 0. That is why we have taken it to be equal to 0. So here is the basic idea of this approach, describing function analysis approach. The approach is, if your system is given in this form, or if it can be brought into this form, then for this particular system, assume a periodic solution. That is, assume this, for example, x of t to be equal to a sinusoidal signal. And then the next step is to approximate the nonlinearity with a quasi-linear function. We shall explain this term. So what is meaning of this second step? We approximate this nonlinearity by something which is similar to a linear function. We call it quasi-linear function. It will not be exactly a linear function. It will be something similar to a linear function. So in the second step, we approximate this nonlinearity by a quasi linear function. And then as a third step, check whether this assumed solution is the actual solution to the system or not. This is also the procedure which we follow for solving differential equations, linear differential equations. Only this intermediate step is not there. In solving ordinary differential equations, linear differential equations, what is the procedure? You assume a solution to differential equation, then substitute that assumed solution into the differential equation. If that assumed solution satisfies the differential equation, that is the solution, actual solution. So here all the steps are the same. The only difference is this intermediate step, because in linear differential equations the differential equation is linear. Here we have nonlinear differential equation, and we shall approximate the nonlinearity by something which is similar to linear function. So let's explain all these points in more detail. These three steps. So let's again take our familiar equation, this van der Pol equation, and we have already learned that this equation can be brought into this particular form. So we have already learned how to bring this equation into this particular form, where g of s, this transfer function g of s is equal to this transfer function, and w of t is some nonlinear function of state variables. So for this particular system, we assume a periodic solution. Here x of t is equal to a sine omega t. We have assumed a solution to this differential equation, and then we shall perform some intermediate step, and then we shall substitute the assumed solution into the equation to verify whether that is actual solution or not. With this x of t, what is w of t? W of t is equal to minus x square into x dot. X we have assumed to be equal to a sine omega t, so its square is a square sine square omega t. And what is x dot? The derivative of x. The derivative of x is equal to a omega into cosine omega t, which is written over here, which is the same as this one. This term a omega cosine omega t, that is written over here. A square is here, and minus sign is already there. Sine square omega t is equal to this expression, as you already remember. If you do not remember, this identity is well familiar to you. Cosine 2 omega t, that is equal to cosine omega t plus omega t. Omega t plus omega t is 2 omega t, which is cosine square omega t, because if we expand it, we get cosine omega t multiplied by cosine omega t minus sine omega t multiplied by sine omega t. These are basic identities. You are quite familiar with these identities. So that is equal to cosine square omega t minus sine square omega t. And what is cosine square omega t in terms of sine? That is, this thing is equal to 1 minus sine square omega t, and this term is over here. Then this is equal to 1 minus 2 sine square omega t, and that is, if we bring this 2 sine omega t to the left hand side and this cosine omega t to the right hand side, we have this relation, and then sine square omega t is this thing divided by 2, which is written over here. Simply multiply the things. This a square into a is a cube, and then omega, this 2 is already also taken outside. So 1 multiplied by cosine omega t is over here, and cosine 2 omega t multiplied by cosine omega t, that is written over here. Actually, why we are doing all these things, that will be clear from the next steps. This term can be further rearranged to write into this particular form. This cosine omega t is already there, and this cosine 2 omega t multiplied by cosine omega t, that is written over here. How it is equal to this thing? You know that cosine 3 omega t plus cosine omega t, that can be written into this form. This is cosine, this is 3 omega t plus cosine, this is omega t. Just expand it. What do you get over here? By using the identities, you have cosine 2 omega t into cosine omega t minus sine 2 omega t into sine omega t. This thing expanded, and likewise this thing expanded, you have this one. This term cancels out with this one, so you have 2 multiplied by this thing. So this thing is equal to this thing, which is written over here. And then this w of t, by some additions, this term outside, we have also brought this 2 outside this bracket. So here we have 2 cosine omega t, 2 cosine omega t minus this cosine omega t. We have 1 multiplied by cosine omega t written over here, and then this minus cosine 3 omega t minus cosine 3 omega t. This 2 is brought outside the bracket. So that is, w of t is equal to this thing. For x of t equal to this thing, w of t is given by this expression, which is approximately equal to this thing. Why this is approximately equal to this thing? Here what we see is that this system, this transfer function, is a low pass filter, and almost all real physical processes, all of them are low pass filters. Low pass filters mean it will suppress the higher order harmonic. It will only pass the first harmonics. Higher order harmonics will be suppressed. That is, this w of t is approximately equal to this thing. Is not exactly equal to this thing. Here is approximation, and we shall also study the effects of this approximation. What we have done is that, in whole of this thing, is that here we have for x of t to be equal to a sinusoidal signal, w of t is something like this one, which can be rewritten in this form: a square by 4 into the derivative of this expression. The derivative of this expression, what is that? Derivative of a sine omega t, that is a omega into cosine omega t. So that is over here, which can also be written in this form: a square by 4 into derivative of minus x of t. Is it clear? This was the assumed solution x of t. What is its meaning? its meaning is over here. W of s will be this thing multiplied by minus x of s. That is, this diagram is approximately equal to this diagram. Where is approximation? Why we have written it to be approximately equal to this thing? Because here higher order harmonics are omitted, these are ignored. These two diagrams are not exactly equal, these are approximately equal. So what we have done is that here was something nonlinear. We have approximated it with something which is similar to linear. Why I use the word similar to linear? Why not exactly linear? You know that in the transfer function, the effect of input is never there. Here, if you have this transfer function, so input, the amplitude of input does not appear over here, right? This transfer function is independent of the input. However, this function that depends upon the input as well, amplitude of the input. Here input was this x of t was equal to a sine omega t. So it depends upon the amplitude of the input. Therefore, this is not linear, this is quasi-linear, something similar to linear but not actually linear. And we call this function the describing function. Compared to transfer function, in transfer function what is situation? In transfer function is independent of the amplitude of the input. Here this thing is not independent of the amplitude of the input, therefore we call it describing function. This describing function may depend upon amplitude and the frequency of the input. So describing function is generally denoted by this n, and this can depend upon the amplitude of the input, it can depend upon the frequency of the input. With this approximation, this differential equation is approximately equal to this equation. This differential equation and this block diagram are the same, right? And this block diagram is approximately the same as this one, and this block diagram is described by this equation. What is this equation? X is equal to, here this is x is equal to this transfer function multiplied by the input. So x is equal to g of j omega, this transfer function multiplied by the input to this thing, where w, what is w? W is equal to this describing function multiplied by this thing, Laplace transform of this thing, written over here. So that is written over here. This block diagram is described by this equation. What does that mean? This equation is approximately the same as this equation. This equation can be rewritten in this form by simply substitution of g of j omega over here. This is g of s. G of j omega can be obtained by substituting s equal to j omega, which is substituted over here, and then this describing function is equal to a square by 4 into s. So a square by 4 multiplied by j omega multiplied by minus x. And then if we bring all these terms to the left hand side and take x to be common, then this is the equation. Can you solve this equation for different for a and omega? How to solve this equation? This is a complex equation. This is a complex equation. To solve it, you will substitute the real part of this equation to be equal to 0 and the imaginary part of this equation to be equal to 0. So this equation rewritten over here, simply what we have done is we have written this thing and this thing together over here, and then solve it by substituting the real part to be equal to 0 and imaginary part to be equal to 0, and we get a equal to 2 and omega equal to 1. That is, the solution to this equation is a sinusoidal signal with the amplitude equal to 2 and frequency equal to 1. So solution of this equation is a sinusoidal signal with this amplitude and this frequency. What about the actual equation? This equation is approximately equal to this equation. So therefore, what we expect is that in this actual system, there will be periodic oscillations, there will be limit cycle, amplitude of those oscillations will be approximately equal to 2, and period of those oscillations will correspond to approximately this frequency. How to solve this equation we have already talked about. We can rationalize this thing, and then this after rationalization we have this expression. You split this equation into two parts, that is real, this is the real part of the equation, and this is the imaginary part of the equation, and from this part what do you get is omega equal to 0 is one solution, and omega equal to 1 is the second solution to this part. If you substitute omega equal to 0, this right hand side comes out to be equal to 0. If you substitute omega equal to 1, this also comes out to be equal to 0. So this is a solution to this part, and then substitute this omega. This is trivial solution. We talk about this solution, substitute it over here, and then we have this relation, and from this relation you can rearrange the terms and finally find the value of a. So this is something which you already know, and hence we have the conclusion is that it is more likely that a limit cycle will exist in the nonlinear system. To summarize the approach, what we do is that if we have some nonlinear system, we bring it into this form, then we approximate this nonlinearity by a quasi-linear function. We call that quasi-linear function a describing function, and then this block diagram will be approximately equal to this block diagram. You substitute the assumed solution is a sine omega t, into this system, and if the assumed solution satisfies that equation, it means that there exist periodic oscillations in the system. So we shall further discuss all these concepts in more details in the next lectures. So any question up to this point? Yes, this approach is applicable to systems of any order, provided that it can be brought into that particular block diagram form.